So today's problems come from chapter 27. This is the chapter with where we introduce magnetic force and magnetic field. And so let's take a look at these examples or these problems. So the first one, problem number 5, the force in a wire is a maximum of 7.50 times 10 to the negative 2 newtons when placed between the pole faces of a magnet. So basically, the force is going from the north, or the field is going from the North Pole to the South Pole. And so you can treat it as being uniform and in one direction in this problem. The current flows horizontally to the right, and the magnetic field is vertical. So that makes it easy enough to visualize. The wire is observed to jump towards the observer when the current is turned on. So what type of magnetic pole is the top pole face? So it's either going to be a north pole or it's going to be a south pole. So if the current, or if the magnetic field points up, it's going to be the south pole at the top. If the magnetic field points down, it's going to be the north pole at the top. Remember, the magnetic field lines point out of north and into south. And so you'll use the right-hand rule to figure out what direction the magnetic field is. So the right-hand rule, point your fingers in the direction of the current, curl them in the direction of the magnetic field, and your thumb will point in the direction of the force. So you're going to have to work backwards a little bit. Your thumb will point in the direction of the force, and your finger will point in the direction of the current. And you'll then curl your fingers in the direction of the magnetic field. And so that'll tell you which pole is north and which pole is south. For part B, if the pole faces have a diameter of 10.0 centimeters, estimate the current in the wire if the field is 0.220 Tesla. So basically, the current, or the field, is acting on the portion of the current that is between the edges of the magnet. And see if the wire is tipped so that it makes an angle of 10 degrees with the horizontal, what force will it now feel? So the angle is going to change, but keep in mind the segment of the wire that's between the pole faces, or the length of segment, will also change. And so see how that affects your answer. So that brings us to the next problem, which is problem 8. A long wire stretches along the x-axis and carries a 3.0 amp current to the right. So you have your L as a vector, or you have I and you have the direction of L. The wire is in a uniform magnetic field. You're given I, J, and K components. Determine the components of the force in the wire per centimeter of length. So you can treat the length of the wire as being 1 centimeter I hat, because it's in the positive X direction. And that gives you enough information to figure out the force from this. That brings us to problem number 18. What is the velocity of a beam of electrons that goes undeflected when passing through perpendicular electric and magnetic fields of 8.8 times 10 to the 3 volts per meter and 7.5 times 10 to the negative 3 Tesla, respectively? So the net force is 0. So there's going to be an electric field. Remember, electric field exerts a force whether the charges are moving or not. And the magnetic field exerts a force on moving charges. So we have the beam of electrons, and so you know what Q is. You're asked to solve for V. Remember, the electric and magnetic fields are perpendicular to each other, and the force, the net force equals 0. So the electric force is equal and opposite to the magnetic force. And so that should give you enough information to figure out what the velocity of the electron has to be. And so what is the radius of the electron orbit if the electric field is turned off? So you turn the electric field off, And then it's only the magnetic force acting, so it's going to cause the electrons to move in a circle. So with that, what's the radius of that circle? Which brings us to number 19. A doubly charged helium atom whose mass is 6.6 times 10 to the negative 27 kilograms is accelerated by a voltage of 2700 volts. What will its radius of curvature, what will be its radius of curvature if it moves in a plane perpendicular to a uniform 0.340 Tesla field? So you're using the potential difference to figure out what velocity the helium atoms get. And then you figure out the radius of curvature, and then what is its period of revolution. Moving on to number 22, an electron moves with velocity v is equal to 7.0 I minus 6.0 j times 10 to the 4 meters per second in a magnetic field negative 0.80 I plus 0.60 j Tesla. So you're given v and b. They're both in the xy plane, which should tell you something about the direction of the force on the electron. But you're asked to determine the magnitude and direction of the force on the electron. Well, it's a fairly straightforward cross product. Keep in mind the Q is negative because it's an electron. And that brings us to the last recitation problem, which is number 37. A circular coil 18.0 centimeters in diameter and containing 12 loops lies flat in the ground. The Earth's magnetic field at this location has a magnitude 5.50 times 10 to the negative 5 Tesla and points into the Earth at an angle of 66.0 degrees below a line pointing due north. So the magnetic field has a north component, so that's positive I, and a downward component, that's negative K. And so we'll define, rather, the north component is positive J, and the downward component is negative K. You'll have an east-west component, so east is the positive X direction, north is the positive Y direction, and up is the positive Z direction. So keep those in mind when you're doing this. And if a 7.0 amp clockwise current passes through the coil, determine the torque on the coil and which edge of the coil rises up, north, east, south, or west. So there are a couple of ways you can think about this problem. You can think about this qualitatively. You can figure out the direction of the torque vector if you know the direction of the torque on the, or the direction of the current, and or rather, you can figure out the direction of the magnetic dipole moment from figuring out the direction of the current, and then you can figure out the torque that way. So you use the right-hand rule to get the magnitude and direction of the dipole moment. Remember, it's a clockwise current, and the loop of wire is on the Earth's surface, which means the XY plane. So that'll let you figure out the torque on the coil. And remember, the torque points in the direction of the axis of rotation, not the actual rotation. You figure out the rotation using another right-hand rule. You point your thumb in the direction of the torque vector, your fingers will curl in the direction of the angular acceleration. And then which edge of the coil rises up, north, east, south, or west? So again, you apply the right-hand rule after you figure out in vector form the answer to part A, and that will give you part B. So it's a combination of math, and it's a combination of knowing when to use the right-hand rule to figure out the direction qualitatively. And that brings us to the 4 homework problems. The first one is problem number 10. So a 2.0 meter long wire carries a current of 8.2 amps and is immersed in a uniform magnetic field. When the wire lies along the x-axis, you get one magnetic force, and when it lies along the y-axis, and so it's pointing, when the current goes in the positive x direction, when the current goes in the positive y direction, you get a different force. And you're asked to find B from that information. The next one is number 23, a 6.0 mega electron volt proton. So that's the kinetic energy of the proton, from which you can figure out the velocity. Enters a 0.20 Tesla field in a plane perpendicular to the field. What is the radius of the path? So you figure out the velocity, you figure out the radius of the circular path. Number 24, an electron, remember an electron is a negative charge, experiences the greatest force as it travels 2.8 times 10 to the 6 meters per second in a magnetic field when it is moving northward. So we know the maximum force when the electron is moving northward. V and B have to be perpendicular for it to experience the magnetic force. The force is vertically upward, and you're given the magnitude. And you're asked to figure out the magnitude and direction of the magnetic field, and you have enough information to solve that. And that brings us to our last problem, number 39. A 15-loop circular coil. So with the magnetic dipole moment, the number of loops in the coil, it works as a multiplying factor. So mu is equal to I times A if it's one loop. If there are multiple loops, or if there are n loops, then U is equal to n times I times A. So you'll need that to figure out the magnetic moment. The current in each loop of the coil is 7.6 amps clockwise. So again, use the right-hand rule to figure out the direction of the magnetic moment. And an external magnetic field, so you're given the magnetic field passes through the coil. So determine the magnetic moment of the coil, so that's magnitude and direction. That's part A. B, the torque in the coil due to the external magnetic field, so that's mu cross B. So once you figure out mu, you apply the cross product. That gives you the torque vector. And then the potential energy U of the coil in the field. Well, that's negative mu dot B. So you're going to probably get a slightly different answer in that case. And so you have mu cross B for the torque, and then the potential energy U is mu dot B. Okay, so those are your problems. If you have any questions, do not hesitate to email me. Otherwise, good luck. I expect videos of the recitation problems up in the discussion section on Blackboard tomorrow. And the homework is due on Monday, as always.